The Gravitational Slingshot Maneuver, a cosmic boost for spacecraft. Introduction. The vastness of space has always fascinated humanity. From the earliest stargazers to modern-day astronauts, the dream of exploring the cosmos has driven us to develop incredible technologies. One such innovation is the Gravitational Slingshot Maneuver, a technique that allows spacecraft to travel farther and faster while conserving precious fuel. Today, we'll dive deep into the science behind this maneuver, its applications, and how it has revolutionized space exploration. Chapter 1. What is a gravitational slingshot? A gravitational slingshot, also known as a gravity assist, is a maneuver used by spacecraft to gain speed or change direction by exploiting the gravitational pull of a planet or other celestial body. Imagine a spacecraft approaching a planet like Jupiter. As it gets closer, the planet's gravity pulls it in, accelerating the spacecraft. Once the spacecraft swings around the planet, it is flung back into space, now moving faster than before. This process is akin to a slingshot, where the planet's gravity acts as the elastic band, propelling the spacecraft forward. At first glance, this might seem like a cosmic free lunch, a way to get something for nothing. But in reality, the physics behind the maneuver is grounded in the fundamental laws of conservation of energy and momentum. The planet's immense mass compared to the spacecraft ensures that its own orbit remains virtually unchanged, while the spacecraft gains a significant boost in speed. Chapter 2. The physics behind the maneuver. To understand how a gravitational slingshot works, we need to revisit some basic principles of physics. The maneuver relies on two key concepts: conservation of momentum and conservation of energy. 1. Conservation of momentum. Momentum is a measure of an object's motion, calculated as the product of its mass and velocity. In a closed system, the total momentum remains constant. During a gravitational slingshot, the spacecraft and the planet interact gravitationally. While the spacecraft gains momentum, the planet loses an infinitesimally small amount due to its enormous mass. This exchange ensures that the total momentum of the system is conserved. 2. Conservation of energy. Energy cannot be created or destroyed, only transferred or transformed. As the spacecraft approaches the planet, its kinetic energy increases due to the planet's gravitational pull. After the flyby, the spacecraft's kinetic energy is higher than before, allowing it to travel faster. The key to the maneuver's success lies in the relative motion of the spacecraft and the planet. In the planet's frame of reference, the spacecraft follows a hyperbolic trajectory, entering and exiting its gravitational field at the same speed. However, in the Sun's frame of reference, the spacecraft's velocity combines with the planet's orbital velocity, resulting in a net increase in speed. Chapter 3. A hypothetical example: slingshot around Jupiter. Let's consider a hypothetical scenario where a spacecraft performs a gravitational slingshot around Jupiter, the largest planet in our solar system. Jupiter has a radius of approximately 143,000 kilometers and orbits the Sun at an average speed of 13.1 kilometers per second. A spacecraft with an initial speed of, say, 10 kilometers per second approaches Jupiter for a gravity assist. In Jupiter's frame of reference, the spacecraft follows a hyperbolic path, entering and exiting its gravitational influence at the same speed. However, in the Sun's frame of reference, the spacecraft's trajectory is tilted, and its velocity combines with Jupiter's orbital velocity. After the flyby, the spacecraft's speed could increase to over 20 kilometers per second, depending on the angle and distance of the approach. This boost allows the spacecraft to reach destinations in the outer solar system, such as Saturn, Uranus, or Neptune, with significantly less fuel than would otherwise be required. Without the slingshot, missions to these distant worlds would be far more challenging and costly. Chapter 4. Historical applications of gravitational slingshots. The gravitational slingshot maneuver has been used in numerous space missions, enabling spacecraft to reach distant targets that would otherwise be inaccessible. Let's explore some of the most notable examples. 1. Voyager missions. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, used gravitational slingshots to explore the outer planets. Voyager 1 performed flybys of Jupiter and Saturn, while Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune. These missions provided humanity with its first close-up views of these distant worlds and their moons. 2. Galileo mission. The Galileo spacecraft, launched in 1989, used a gravity assist from Venus and 2 from Earth to reach Jupiter. This complex trajectory allowed Galileo to study Jupiter and its moons in unprecedented detail. 3. Cassini mission. The Cassini spacecraft, launched in 1997, used gravity assists from Venus, Earth, and Jupiter to reach Saturn. Cassini spent over a decade studying Saturn, its rings, and its moons, including the enigmatic Titan. 4. New Horizons mission. The New Horizons spacecraft, launched in 2006, used a gravity assist from Jupiter to reach Pluto. This maneuver allowed New Horizons to achieve the fastest launch speed of any spacecraft and provided valuable data about Pluto and the Kuiper Belt. These missions demonstrate the versatility and importance of gravitational slingshots in space exploration. By leveraging the gravity of planets, scientists can design trajectories that maximize scientific return while minimizing fuel consumption. Chapter 5. The mathematics of gravitational slingshots. While the concept of a gravitational slingshot is straightforward, the mathematics behind it can be quite complex. Let's break it down step by step. 1. Relative velocity. The spacecraft's velocity relative to the planet is crucial. As the spacecraft approaches the planet, its velocity vector changes direction due to the planet's gravity. The angle of approach and the distance from the planet determine the magnitude of the velocity change. 2. Energy transfer. The spacecraft gains kinetic energy from the planet's orbital motion. This energy transfer is most efficient when the spacecraft's trajectory is aligned with the planet's orbital direction. 3. Hyperbolic trajectory. In the planet's frame of reference, the spacecraft follows a hyperbolic path. The shape of the hyperbola depends on the spacecraft's speed and the planet's gravitational pull. 4. Velocity addition. In the Sun's frame of reference, the spacecraft's velocity after the flyby is the vector sum of its velocity relative to the planet and the planet's orbital velocity. These calculations require precise measurements and simulations to ensure the spacecraft follows the desired trajectory. Even small errors can lead to significant deviations, highlighting the importance of accurate planning and execution. Chapter 6. Challenges and limitations. While gravitational slingshots offer numerous advantages, they are not without challenges and limitations. 1. Timing and alignment. The maneuver requires precise timing and alignment. The spacecraft must arrive at the planet's location at the exact moment when its trajectory aligns with the planet's orbit. This often involves years of planning and precise navigation. 2. Gravitational perturbations. Other celestial bodies, such as moons or nearby planets, can perturb the spacecraft's trajectory. These perturbations must be accounted for to ensure a successful flyby. 3. Communication delays. For missions to the outer solar system, communication delays can make real-time adjustments difficult. The spacecraft must rely on pre-programmed instructions and autonomous systems. 4. Limited opportunities. Gravitational slingshots are only possible when the spacecraft's trajectory intersects with a planet's orbit. This limits the number of available opportunities and requires careful mission planning. Despite these challenges, gravitational slingshots remain a powerful tool for space exploration, enabling missions that would otherwise be impossible. Chapter 7. Future applications. As humanity looks to explore deeper into the solar system and beyond, gravitational slingshots will continue to play a crucial role. Here are some potential future applications. 1. Interstellar missions. Gravitational slingshots could be used to accelerate spacecraft to speeds necessary for interstellar travel. For example, a slingshot around Jupiter could provide the initial boost for a mission to Alpha Centauri. 2. Asteroid deflection. In the event of a potentially hazardous asteroid, a gravitational slingshot could be used to redirect a spacecraft to intercept and deflect the asteroid. 3. Lunar and Martian missions. Gravitational slingshots could optimize trajectories for missions to the Moon and Mars, reducing travel time and fuel consumption. 4. Space telescopes. Future space telescopes could use gravitational slingshots to reach distant observation points, such as the Sun-Earth L2 Lagrange point. These applications highlight the enduring importance of gravitational slingshots in advancing our understanding of the universe. Chapter 8. The Cosmic Perspective. The gravitational slingshot maneuver is a testament to humanity's ingenuity and our ability to harness the forces of nature. By leveraging the gravity of planets, we can explore the farthest reaches of our solar system and beyond. This technique not only saves fuel but also opens up new possibilities for discovery and exploration. As we continue to push the boundaries of space exploration, the gravitational slingshot will remain a vital tool in our cosmic toolkit. It reminds us that even in the vastness of space, we are connected to the celestial bodies around us, and by understanding their motions, we can unlock the secrets of the universe. Conclusion. The gravitational slingshot maneuver is a remarkable example of how physics and engineering come together to enable extraordinary achievements. From the Voyager missions to future interstellar travel, this technique has transformed our ability to explore the cosmos. As we look to the stars, we can be confident that the gravitational slingshot will continue to propel us forward, one planet at a time.